In this module, we will learn about vectors. Let us start by understanding the differences between scalars and vectors. A scalar quantity just has a magnitude. There is no direction associated with a scalar. There are many quantities in physics which are scalars, such as time, length, mass, temperature, speed. Scalars are manipulated by rules of ordinary algebra. In contrast, a vector quantity has both a magnitude and a direction. For example, the position of a particle, the velocity of an object, these are all examples of vectors. So if you are describing the motion of an aeroplane, if you just specify its speed, it's incomplete information. It's unclear whether the plane is traveling north or south or east or west in any direction. So you need to specify the direction of the aeroplane as well. So this is done through its velocity, because velocity has a magnitude, which is the speed, but it also has a direction. It tells you in which direction the plane is traveling. So vectors have their own rules of manipulation. They don't always follow the rules of ordinary algebra. Vector notation. So vectors are denoted by a number of symbols. For example, arrowheads are used. Sometimes under tilde are used. Sometimes bold font letters are used to represent them. And for example, to represent unit vectors, the hat symbol is often used. In a coordinate system, vectors need not always start at the origin. In fact, if there is a particular vector pointed with an arrow, for example, you can translate it anywhere in the coordinate system as long as its magnitude and its direction remains the same. That means you can translate this arrow into anywhere in this coordinate system, as shown in this diagram. Identical vectors. Equality of two vectors. Basically, if two vectors are equal if their magnitudes and directions are the same. That means all these parallel vectors shown in these figures are equal because they have the same length and they point in the same direction. It does not matter where they start and where they end, as long as their sizes or lengths are the same and their directions are the same. They are all equal. Unit vectors. A unit vector has a length of 1 unit and they point along a specific coordinate axis. For example, the unit vector along x in the Cartesian coordinate system is represented by I with a hat symbol, and the unit vector along the y direction is represented by j with a hat symbol. So vector components. A vector in general, a vector r is written as rx times I hat plus ry times j hat. Here rx and ry are called the vector components. They simply specify the lengths in the x direction and the lengths in the y direction in units of I and j. And what is the length of the vector r, the magnitude of vector r? It's given by the Pythagorean theorem, square root of rx square plus ry square. And this is seen from this figure. Rx and ry makes a right triangle and the hypotenuse gives the magnitude of r. How do we add and subtract vectors? So there are two ways to do that. One is graphically, the other one is algebraically. Let us first look at the graphical method. So over here in this figure, you are shown two vectors a and b pointing in two different directions and having two different lengths. The way to add a and b is to translate one of the vectors. For example, in this case, we keep a fixed and translate b so that it starts from the head of a. And then we need to draw a third vector from the tail of a to the head of b to complete the triangle. And it is this vector that gives the sum of a and b vectors. This is called the resultant vector. How do we subtract vectors? So for subtraction, we have to negate one of the vectors. For example, we have to represent minus b if we are to calculate a minus b. And when we negate a vector, it simply means that we change the direction of the vector by 180 degrees. So the length of b remains the same. And this is seen in this other figure here. And now once we have represented minus b, we can simply use the addition rule as before to calculate the resultant vector, the sum of the vectors, simply by translating minus b to start from the head of A. Perhaps an easier way to add vectors is to use their components. In this case, we simply add the corresponding components. If we are to add A and B, we just add the x components of A and B, and they point in the I direction, and then we add the y components of A and B, they point in the j direction. So the vector is given by ax plus bx in the I direction, ay plus by in the j direction. And the same thing for a minus b, we just subtract the corresponding components. We subtract the x components and the y components. Vector addition is commutative. That means it doesn't matter whether you add a to b or b to a, the result is the same. And you can check this if you do this graphically as shown in the previous slides. You will see that you get the same result in vector. Multiplication, there are a number of ways to multiply a vector. First, let us look at the case where we have a scalar multiplying a vector. The scalar here is s and the vector is a, and the vector has three components in the three axes, I, j and k representing the z axis. And we simply multiply the scalar with each of the components. So the resulting vector is s times ax pointing in the I direction plus s times ay pointing in the j direction plus s times az pointing in the k direction. This simply means scalar s basically changes the length of the vector, its direction remains the same. So either it magnifies or it shrinks the vector in size. It is also possible to multiply one vector by another vector, and there are two possible results. So in one case, it is called the dot product. When two vectors are multiplied in this manner with the dot product, you get a scalar quantity out. So this is also called the scalar product. And this is given by this definition, a dot b. A dot represents the scalar product. A dot b is equal to the length of a times the length of b times cosine of the angle between a and b. This is also shown pictorially in this figure. This simply means we have to take the projection of one vector along the other vector and multiply the two to get the dot product. So what happens if the two vectors are pointing in the same direction? Then theta is 0 and cos of 0 is 1. So we get the maximum value for the dot product, which is just the product of the magnitudes of a and b multiplied. What if theta is equal to 90 degree, the vectors are perpendicular to each other? Then cos 90 degree is 0 and the dot product is also 0. So perpendicular vectors result in a 0 dot product. The dot product can also be computed or calculated component wise. You just simply multiply the corresponding components and add them up. For example, in this case, the dot product is written as ax times bx plus ay times by. So dot products are commutative, so it doesn't matter whether you do a dot b or b dot a, the result is the same. Dot products are also distributive. That means if you take the dot product of a with the sum of b and c, it's the same as taking the dot product of a with b and adding it to the dot product of a with c. So you can see that the dot product is distributed throughout the sum of b and c. So this is the distributive law of multiplication for dot products. Then let us look at the other way to multiply two vectors. This is called the cross product or the vector product. So when the vectors are multiplied in this manner, we get another vector as a product. In this way, it's different from the scalar product. The scalar product gives you a scalar quantity, but the vector product or the cross product gives you a vector quantity. And it is defined by this equation, the magnitude of a cross b, the product of the magnitude of a and the magnitude of b, and sine of the angle between a and b. Note that the sign of the angle is important in this case. So if a and b are pointing in the same direction, then the magnitude of the scalar of the cross product is 0. Sine 0 is 0. And if the two vectors are perpendicular to each other, sine 90 degree is 1, and the magnitude of the cross product becomes magnitude of a times magnitude of b. And so since this results in a vector c, the cross product results in another vector, in this case represented by c. C is actually perpendicular to both the vectors a and b. So if a and b lie on a plane, lie on the xy plane, C points in the z plane. In this way, C is perpendicular to both A and B. And the cross product can also be calculated in the component form. So if we just multiply, if we have two vectors A and B with 3 components each, and we multiply every component with every other component between the two vectors, and then we can use the definition of the cross product. So a I cross I will give us 0, because sine of the angle between the two vectors I is 0. But if you have I cross j, for example, then the sine of the angle between the unit vectors and I and j is 90 degree in this case. If it were j cross I, it would be minus 90 degree. So you will get a sign change. So, and we know the vector will point perpendicular. So if you do I cross j, you get a vector in the k direction, and you get the product ax by out. So in this way, if you write out all the components, you end up with this result, ay bz minus by az for the I component, and the rest is shown in the slide here. The cross products are important for evaluating many quantities in physics. Both cross products and dot products are important. Dot product we will use when we talk about energy, when we have to compute or calculate work done by a force. And the cross product we will use cross product when we are evaluating torques that create rotational motion, or for example we calculate angular momentum of a turning object. So we will use the cross products. Also, when we go to electricity and magnetism, we will use these quantities frequently. We will use these methods of multiplication quite frequently.